Okay, guys, today we're going to start our discussion about gravity by doing a quick demonstration. And what I would like to see is, do all objects fall at the same rate? Now, if you were to read our textbook, you would see that they do say that that is true, that all objects do fall at the same rate. But I just want to double check and see if that's true. So we're going to see if this textbook will fall at the same rate that this piece of paper falls at. We're going to put a pillow down here just to make sure that we don't damage the book or the floor. I'm just going to say 3, 2, 1 and drop them. We'll see if they fall at the same rate. 3, 2, 1. So it was quite a difference. They did not fall at the same rate. So right now you can pause the video if you want to take a moment to think about why they don't fall the same way. Ultimately, the big issue, and this is something that has really perplexed people for really all of human history, is how friction and how air resistance act on things all the time. And so the issue with these is that they do actually fall at the same rate. I'm going to demonstrate. I can make this piece of paper fall at the same rate that the book falls at. But there is this issue with the air resistance, or it's sometimes referred to as the drag force. And that is because as the book falls, all of the air molecules that are underneath it, at the moment that it passes through, they have to get out of the way. They can't go through the book. So they're going to get knocked out of the way. And as they get knocked out of the way, they add resistance to the book's motion. Now, the book is pretty good at resisting it because it's pretty dense and has quite a bit of weight to it. The piece of paper I purposely chose because I wanted something that was the same surface area. So as they fell, they would have fallen through the same surface area approximately. And you can see that when I did that, that made the paper fall much, much more slowly. So what you might do right now is to think about, you could pause the video, to think about what could you do in this situation that might make that so that the paper would fall at the same rate as the book. So if you want to pause the video to think about it, then we'll discuss some of those possibilities. This is my first solution. If I want to make sure that the air molecules don't act on the paper at all, I'll just put them on top of the book. Now, this is not connected to the book in any way. The piece of paper can slide off. If I tilt the book, the piece of paper will slide off, but the piece of paper will now no longer feel the air resistance, and so it should fall at the same rate as the book. So let's check it out and see if it works. All right, so piece of paper is not connected to it. Just laying the piece of paper on top. 3, 2, 1. Fell right along with it. Let's try it one more time. 3, 2, 1. Okay, that seemed to work pretty well. Now, some people might say, oh, there's kind of like an air effect where there's like a vacuum being created by the book. And that is true. There is kind of an effect that does kind of help the piece of paper stay on the piece of book. So let's take away that advantage and let's make the piece of paper feel the air again. And this time, what I'm going to do to make the piece of paper a little bit better is I'm going to crumple it up. And by crumpling this up, I'm going to make it more dense. I'm going to give it a smaller surface area. So now it's not going to run into nearly as many air molecules. I'm making it more aerodynamic. So now it's able to cut through the air and deflect the air molecules sideways instead of pushing them down out of the way. So now, this is as good as we can do with this guy. Is this guy going to be able to fall at the same rate as the book? We'll do it a couple times just so you can see it clearly. All right, here we go. 3, 2, 1. Let's try that one more time. So we can slow this video down and we can see how it worked. 3, 2, 1. So for me, that looks pretty close. So if it wasn't falling at the same rate as the book, it was pretty close. So I would say that we can essentially neglect the air resistance as long as we make the object fairly aerodynamic, relatively dense, have a fairly small surface area. And if it's moving at not too fast of a speed, then we can pretty much ignore the air resistance. And you can see from the demonstration that it really works. Even with a piece of paper, I can make this piece of paper fall at the same rate as a book or a brick or a rock or anything that you want to give me. I can make it fall at the same rate. So let me present some information to you that will kind of help you further understand how that's going to play out in the problem solving side of things. All right, so let me present some information that I think you will find helpful. All right, so this document is available to you. You can go and look at it anytime. It's shared in Google Classroom. And essentially, what I'm going to kind of do is show you how does this thing that we just saw happen, how does that play out for the problem solving when you're trying to solve problems with objects free falling. And so that simply means objects that are falling near the surface of the Earth and no other object is influencing them other than gravity. That's the idea of being in free fall means that you're the falling portion, but no other thing. Nothing supporting from below, and there are no other forces that are acting on you. So all objects do accelerate at the same rate, and we have measured that value very accurately and know that that value is 9.80 meters per second squared. But that value only applies if either there's no air resistance. So one of the ways that we could have made this demonstration work where the piece of paper falls the same as the book is to take all the air out of the room. Obviously, I'd have to get out of the room to be able to do that. I can't really pull that off in my house here. But if we could remove all the air, you would see that, yeah, the piece of paper would fall. Even if I laid it flat, it would still fall exactly the same as the book. But with that air resistance there, it really changed things dramatically. So that kind of creates this question, when can you ignore the air and when can you not ignore the air? The air is, of course, always there. And it's always going to cause a slight difference in what we'll calculate in this class compared to what you might see in the real world, but it's going to be very close because we're going to create situations that are favorable so that we can use this kind of simple principle to be able to solve real world problems. So the question of when is the air resistance negligible, or when is it so small that we can ignore it? That's what negligible means. Um, well, there's a couple of things we could do. So first of all, one of the things I did with the paper when I crumpled it up was I made it denser. So now the mass is contained in a smaller volume and then also in a smaller area. So again, making the object smaller. So if I had two marbles, one was bigger and one was smaller, well, the smaller one's going to feel less air resistance. Even though they have the same density and they have the same shape, but there's going to be a big difference in what the bigger marble is going to feel. So making it more aerodynamic. So that means making it pointed or making it so that when it moves through the air, instead of pushing the air forward, it kind of deflects the air sideways. And that requires much less force if it just deflects the air slightly sideways rather than pushing the air out of the way. And then the other thing that is really helpful is if we don't allow it to fall too far. So I don't know how far is too far. It depends on the object. You can see with the paper, I mean, I don't know, I would say a few inches would be enough that the piece of paper, you would notice that it's not falling the same way as the book. I mean, it was almost immediately obvious. In other cases, like a marble or a baseball, if you drop that, you'd have to let it fall a pretty good distance before the air resistance. You will start to notice that it's no longer accelerating. It has stopped accelerating because of the gravity, because other forces are now acting on the object. So for our purposes in the classroom or in your house, if I were to, for example, drop a pen, we can ignore the air. I assure you, our number will be dead on accurate. The air resistance will be so little acting on a pen over the small distance, the small speed that it moves at, we won't really have to worry about it at all. So for the most part, we will be ignoring the air resistance, whether that's valid or not. As a simple model, we'll ignore the air resistance so we can make the calculations of velocities, distances, times, all these things that we want to know about the motion of the objects. So now what I'd like to do is to walk you through sort of three areas that you're going to see in terms of problem solving. And this is just the way that we've broken the ladder down. I'm talking to different classes, so you may hear me make reference to both honor and regular, and then also to the IB classes. And so just kind of pay attention to what part applies to you. All of this applies to solving problems involving gravity, but it's at different levels. We'll go to different levels of both the complexity of the problem and then the complexity of the math that you have to use to solve the problem. So let's first start at what without a doubt would be a level one, and that is simple free fall problems. This is level one for gravity though. Okay, and I'll tell you what the levels are for the regular honors and the IB classes. So in this, what makes this very simple is that we're only going to allow it to fall in one direction. So essentially, we're going to drop something, we're going to release it or let it go, or it's going to fall over, something like that, and it's going to fall only in the downward direction. So when an object falls only in the downward direction, that means that every single property, whether it's the displacement, the velocity, or the acceleration, they will all be pointing in the downward direction. So in that situation, it's our right as the physicist to choose whatever frame of reference we want to make our measurements from. So long as we choose a frame of reference and we always make our measurements in that frame of reference, everything should work out fine for us. And so the smart thing to do is to make down the positive direction. Because if down is the positive direction, then we can treat it kind of like the early problems that we looked at with acceleration, where we just looked at objects accelerating in one direction. maybe speeding up or slowing down, but always moving in the same direction. And we're going to do the same thing with gravity now. We'll only look at it moving in one direction. And that really simplifies things quite a bit. Um, and so the simplification ultimately is that you would choose the downward direction to be the positive, and then you don't have to worry about the positive or negatives at all. Everything is going to sort itself out. The other thing that you want to pay attention to with problems like this is that one of the things that makes gravity a little more difficult is that you may, for example, be told something like, I dropped this pen and it lands zero 0.3 seconds later. And that's all I tell you. And I ask you to start answering things about it. Like, for example, how high was it when I dropped it? If I tell you how long it took to land on the ground, you should be able to tell me how far this object fell. And you can do that because as soon as I let go of the object, you know the object is in free fall. That means you automatically know the acceleration. So the acceleration is given to you as soon as you know the object is no longer being supported by anything. Even if you throw it upward, it's still considered to be in free fall. But in these problems, we're only allowing objects to fall in the downward direction. So you would want to look for context clues that would give you those additional pieces of information that it seems like you're missing. So if you are told that something is dropped or that it fell or that it was released, then you know it's falling. So you automatically know the acceleration. And the other thing about those words is those words imply that the initial velocity was zero. Now, I say imply because it doesn't guarantee it. I mean, in some ways, some people might use those words in a way where maybe the thing did have a little bit of velocity. When they say they dropped it, maybe they mean that they tossed it, but very gently. And so they did actually give it a little bit of velocity. But for my money, I would take the word dropped, or if you said that something fell or that something was released, that you meant that initially, when it started falling, its velocity was zero. I feel like that's a very safe implication, and any physics books would take it to mean that. Now, the other thing that you might try to do with these problems is to draw diagrams like these. So draw the velocity, you're making your list of given information, but maybe just a little arrow. What is the displacement? Is this thing going to land above where it started, or is it going to land below where it started? What's the displacement look like for this thing? What is the velocity in the beginning? Was the velocity being thrown upwards, or was it being dropped and allowed to fall downward? Was it thrown downward possibly? One thing you can be sure of is that once the object is released, whether it was thrown up, down, or just dropped with zero velocity, the acceleration is 9.8. That is a given. Should absolutely be understood, and is not something that you should need to be able to be told on the test. If you're told that the object is no longer being supported, it's clear the object is airborne, then you would assume that it has begun to accelerate at 9.8 meters per second squared. Okay, so that's what you're going to see mostly at level 1. In the regular and honors, this would be on the ladder for acceleration. This is level 3. And in the IB class, this is level 2. And then level 2 also leads a little bit into these moderate freefall problems. The only difference with the moderate freefall problems is that now we're going to launch the thing upward. And by launching it upward, that means that it's going to go up, it's going to come to a stop, and then it's going to come back down. And so now you have some of the properties that point up and some properties point down. For example, if I throw it upward, the initial velocity is in the upward direction, but the acceleration still points downward. That's why it slows down. Remember, when the acceleration goes against the object, it's going to slow down. When the acceleration goes with the object, it's going to speed up. So since these guys are going against each other, on the way up, the pen's going to go slower and slower and slower until it eventually comes to a stop. And then it'll begin to go down and it'll begin to speed up in the downward direction. That should make sense because the acceleration is in the downward direction. So once it comes to a stop, it will now pick up speed and the velocity will be in the direction of the acceleration, and it will go faster and faster and faster in that direction. So what I try to do to make this a little bit easier to digest instead of throwing everything at you all at once is that we create symmetry by throwing the object up in the air and then having it land back in the same place where it started. And that happens all the time. In baseball, the ball is hit at approximately the same height that the ball is caught at if the ball is hit up in the air. In soccer, if you kick the ball from the ground up into the air, it's very likely going to land right back down on the ground. So it's going to start at one displacement, it's going to go up, but then it's going to come right back and have zero displacement vertically. Vertically, it'll have no displacement. It started on the ground and it ended on the ground. So this is a kind of situation that comes up all the time. This kind of symmetry creates itself naturally anytime you do something on level ground. So a couple of tricks sort of arise when you create this symmetry, where we go to this higher level of problem. And what really makes this a little bit higher level problem is that you now have to have some negative signs. You can't have the velocity point up and the acceleration point down and say that those are both positive. But that's obviously going to create a conflict in the system of reality. So when you have things that are two properties of the five motion properties, you have five of them pointing in opposite directions, then you need to have positive and negative signs. And the obvious choice to make there is to use what you've learned in your math classes. If you're moving up the y-axis, that's in the positive direction. And when you go down in the y-axis, then you're going in the negative direction. So I would just stick with that because that's like very intuitive. That's something that we've seen a lot in our math classes. And so you assign anything that's in the positive direction, whether it's the initial velocity, I could throw this pen up in the air, or I could also throw this pen downward. And in that case, I might make a change in how I do things. But when you have two properties pointing in different directions, you have to deal with the negative sign. So that's what takes us to the next level. You must now deal with the negative sign. You can't just avoid it like we were able to do when the object only moved in one direction. So a few tricks that come out of the symmetry for the most part is that the time that it takes to go up is going to be the same as the time to go down. And that is because what gravity was doing on the way up, taking away from the velocity, it's now going to undo that by giving back to it the speed on the way back down. So on the way up, it's taking away the speed. On the way down, it's giving the speed back. The speed that you start with at the bottom is going to be the same as the speed that it's going to land with on the way back down, except that it'll be pointing in the opposite direction. So in the beginning, it was moving upwards, but in the end, it was moving downward. But so long as they start and they stop at the same level, then you're going to find that the speed was the same. The only difference is that, obviously, if you're talking about landing, you would want to say that that was a negative velocity. Speed-wise, you can say that the speeds are the same. But in case of velocity, velocity cares about the direction. You would say the velocity was negative when it landed. Okay, another thing that has nothing to do with the symmetry is that when the object rises and gets to its highest point, it will have zero velocity. It's going to go from moving in the positive direction to moving in the negative direction. You can't go from the positive side of the number line to the negative side of the number line without passing the zero. So it's not going to stop there. It won't be hovering and spinning and waiting for you to notice it. It's for just the briefest of instance, it's going to come to a stop and start moving back down. But when it's at that point, it moves very slowly because it's obviously it doesn't come to a stop instantly. It slowly comes into that position of zero velocity. And so when the object is up at the top, it's moving very slowly. That's like the place where you can kind of really make observations of it. And then it's going to pick up speed as it comes back down. The last thing, and this could come in helpful with certain problems, I would say this is like getting a little bit on the higher level for this type of problem. But using the fact that the displacement is zero, you can actually use that to solve a lot of things about the problem. You could figure out what the initial velocity was. You could figure out how high the thing went. It depends on what information that you were given. But there are instances where knowing that the final velocity, it started and stopped at the same place, you can actually use that to solve problems. So that's what makes these a little bit more challenging, is the fact that you have things going both up and down. Your properties pointing in opposite directions. Now you have to deal with that negative sign. There's no way to get around it. The last thing, and this would be if you get at the highest level, so this is for the IB level 4, and for the regular and honors, this is a little bit of this aspect. However, generally speaking, the level 4 is going to be these moderate level problems. If you can make it to these, then you'll make it to level 4 in the regular and the honors classes. These questions are available, though, to anybody who is interested in looking at these problems. You can absolutely feel free to ask me to look at these worksheets. The complex free fall problems, what's going to make them complex is that we're going to take away your symmetry. So instead of letting it go up and land at the same height, we're going to let it fall down to a lower level. So instead of going up like this and landing here, we're going to let it continue all the way down. So that could be something like you toss your keys up in the air, and then your keys, instead of landing in your hands, you miss them and they fall to the ground. So they no longer have landed at the same level. So now the speed at the start and the end are not the same. The time to go up and the time to go down, they're not the same. It's still zero velocity at the highest point. That's still true, of course. But ultimately, now the displacement is not zero. So now there is either a positive or a negative displacement. So let's take a look at this first example, the one on the left. In this situation, we're maybe standing on the top of a cliff or on an edge, or we just throw something like our keys up in the air, but then we miss them, and on the way down, they land all the way down where our feet are. So that's a situation where I would have a negative displacement. I landed at a position that was lower than I started from, so therefore I now have a negative displacement. I have moved in the negative direction. That was the result of my motion. On the other hand, you can imagine throwing something up to somebody. So maybe somebody was up on either like in a window or maybe up on like a patio or something, and you toss a drink or something up to them. So now the thing is going to move up and it's going to land and finish at a higher height with a positive displacement. And that's what the second set of arrows is demonstrating. Objects might move upward, come to a stop, and then start to move back down, but then become stopped by either landing on something or somebody grabbing that object. So the problem with this is that now all of the simplifications that we've been using up until this point, which included the initial velocity being 0, back at those first simple problems, we looked for context clues that oftentimes told us that the initial velocity was 0. And when you take away the v naught t, this now becomes just simple algebra. You can solve for the time with algebra. At the middle level, the moderate level, you can plug in 0 for d. And in that instance, actually, you'd see that you can still solve for things, and you'll see some cancellation. Even when the displacement is 0, you can use that to solve. Now, in this case, nothing is 0. The displacement is not 0. It's either some positive or negative value. Of course, the acceleration is not 0 because we wouldn't be using this equation if we didn't have any acceleration. And in this case, the initial velocity is not 0. We're either going to throw the object upwards, or we could even throw the object downwards. That would also, we would use the same exact math. And in that situation, the problem is that it's going to be quadratic, and there's really no way to get around that. This equation will have to be solved using the quadratic equation, but there is another option. So if you didn't feel comfortable with trying to solve it with the quadratic equation, you could kind of try to bypass it. And the only thing where you're going to need to solve for using the quadratic equation is if you're solving for the time. So if I tell you the height of a bridge, and I say I drop a marble and I want to know if I throw it downward with this speed, how long will it take for it to land? That's a very high level problem. It requires you to use either the quadratic equation or you use this to bypass it. So instead of using the quadratic equation, you solve for the final velocity. Of course, if I just threw something down from the top of a bridge, how would I know what the final velocity is? I might be able to tell you how fast I threw it, but I probably wouldn't be able to tell you how fast it was moving when it landed. So the bypass would say, let's go for the final velocity, and I'll use the equation v squared equals v naught squared plus 2ad, and I'll use that to come up with the final velocity. And once I have the final velocity, then I can go use the equation v equals at plus v naught, and I can solve for the time. So essentially what I'm trying to do is, instead of using one more complex equation that involves using the quadratic equation, I'll use two slightly simpler equations, and I'll kind of bypass that. So it's not a requirement that you have to use the quadratic equation, but these are the highest level problems where you have to have some kind of plan in advance to handle what are you going to do when all the properties have value now, and now you've kind of taken away some of your algebraic options. The d equals 1/2 at squared plus v naught t, kind of loses some of its algebraic options when all of the properties d, a, and v naught when they're not 0. It makes it a considerably more challenging problem.